Here we have two wires that are tied to a zero point 0.3 kilogram sphere. It says the sphere revolves in a horizontal circle at a constant speed of 7.5 meters per second. And it says let's call T1 the tension in the upper string or upper wire, and then T2 is the tension in the lower wire, and it wants us to find the magnitude of T1 and T2. All right, so I'm just gonna go ahead and draw my free body diagram out first. So this is a sphere that's being spun in a horizontal plane here. All right, here's f of g. F of g points down the page. Okay, so these vectors or vector components are not drawn to scale. Here's T1. T1 is going to be pointing towards this supporting beam here. So T1 is a left and up diagonal. So that's T1. It says T1 is the upper string, so I'll just be consistent with that. And then because T1 is a diagonal, it'll have to have components here. T1x is going to point leftward. Okay, and then T1y is going to point up. Just to match the vector itself. The vector for T1 is pointing left and up. So hopefully as you practice, make sure you draw these components out correctly because it does matter. All right, here's T2. T2 is going to be pointing down and left as well. So this is in the third quadrant, so it's going to have a T2x component that is pointing leftward. And then T2y is going to be pointing downward. Okay, so pay attention to how these vectors are placed and then draw the components that correspond to those vectors. All right, other than that, I'm just going to go ahead and get cracking here. To solve for this, I do need to figure out what theta is. So theta in this case, I'm just going to choose. The theta wasn't given to me. It gives me these measurements in the diagram. I'm just going to choose theta touching the x-axis because then I can use x as cosine and y as sine. So nothing crazy. All right, so due to symmetry, I notice here on the left, this is 0.5. The bottom is also 0.5, and both of the wires are 1 meters in length. So due to symmetry, these two thetas are equal. All right, so let's go ahead and find theta real quick. Let's solve for theta, one of the theta. I'm just going to use the upper blue here. So theta is placed here touching the x-axis. So therefore, sine is opposite over hypotenuse. I'm going to use sine because the diagram gives me the opposite leg, which is 0.5 meters. And then I know the hypotenuse, which is the length of the wire, is 1 meter. So I'm going to use sine opposite over height because those are the two legs given to me. So to solve for theta though, I just need to divide both sides by sine or sine inverse. Opposite being 0.5 because in the diagram, opposite of this theta that I'm using is 0.5, and then the hypotenuse is 1. So that's why the 0.5 is in the numerator and the 1 is in the denominator. And if you punch this in your calculator correctly, you should get a value of 30 degrees. Okay, so theta is 30 degrees for the top and also for the bottom. Now, let's go ahead and find T1 and T2 though. Okay, so in no particular order, it's up to you if you want to find T2 first and then find T1, or T1 first and find T2. I'm just going to make these true statements, and if you make these true statements, it doesn't really matter which one you find first. I'm just going to say that the centripetal force for this particular system is composed of T1x and T2x. So if you look at the free body diagram here, you have T1x pointing towards the center of this horizontal plane, and then you have T2x also pointing in the same direction towards the center of the horizontal plane. So as this thing is being spun in a horizontal plane, you have T1x and T2x pointing towards the center of the circle, which is your net force for this particular problem in the x direction, and that is your centripetal force. So your centripetal force is simply composed of two things, T1x plus T2x. Here I can break up Fc into mv squared over r. Here the mass is given to me, which is 0.3. The speed here is given to me as 7.5 in the wording. And then T1x I broke down to T1 cosine. As I stated earlier, I'm going to choose this theta because then x is because this theta touches the x-axis. X is cosine and then y is sine. So this is T1x, so this would just be T1, which is the hypotenuse, times cosine of theta. And then likewise with T2x, T2x is just T2 cosine of theta. Well, I already know what theta is. Theta is 30 degrees, so I'm just going to plug and chuck real quick. Here, I plugged in M for 0.3, V for 7.5. And then you notice here I highlighted R because I don't know the radius of this particular horizontal plane. Okay. Cosine of theta, theta being 30 degrees, so I substitute in theta for both these terms on the right. So I'm just going to simplify just a little bit. Okay. Well, I don't know what R is, but I can figure out what R is super quick by just doing Pythagorean theorem. Here, I know that this is 1 meter because the diagram said so. I know that the opposite leg, okay, is 0.5 meters because it says so in the diagram. So here's my R. Okay. So to find my R, I'm just going to do Pythagorean theorem. This is a right triangle. I have two legs. You also know what the angle is here. The angle here is 30. So it's up to you if you want to do sine and cosine or tangent. But I'm just going to do Pythagorean theorem here because I know the two legs, the opposite leg and the hypotenuse. So to find r, all you have to do is do r squared plus 0.5 squared equals to 1 squared. So a squared plus b squared equals c squared. So here's r squared plus 0.5 squared equals to c squared, c being the hypotenuse, which is just 1 in this case. And if you simplify this, 0.5 squared is 0.25, and then I got to subtract it on both sides to get r squared by itself. So if you do r squared equals, it'll be 1 because 1 squared is 1 minus, this is 0.25 if you square, but this is positive, so when you move to the other side it becomes negative. So 1 minus 0.25 gives you 0.75, but this is r squared, so I need to square root r squared to get r by itself. So the square root of 0.75 is about 0.866 meters. Okay, so that's my radius of this horizontal plane. But now that I know r, I can just do a plug and chug. So here, the highlighted r, I just substitute out for 0.866. But you know, these are on the right side. I noticed that both these terms have a cosine of 30 and a cosine of 30, so I just factor out the cosine of 30. So you can do that as long as the two terms share a common variable. In this case, both terms have a cosine of 30. You don't have to. I just chose to. Okay. So here I'm just going to go ahead and simplify a little bit. If you punch all this on your calculator on the left side, 0.3 times 7.5 squared divided by 0.866, you should get about 19.49. And then cosine of 30 degrees is about 0.866. Once again, all of this is factored out already. So to get T and T1 and T2 by itself, I'm going to divide both sides by 0.866. Okay. So if you take 19.49 divided by 0.866 on your calculator, you should get about 22.5, and it equals to T1 plus T2. But here you have T1 and T2, right? You have a statement that has two unknowns, which is okay. So if you've been practicing physics, this is pretty light work. That triggers that you need to set up your information in the y direction. You can't do anything else with the x information here because you're stuck. You have two unknowns. So the other way to do it is to set up your information in the y direction. So if you can watch the diagram here, I made the statement T1y is equal to f of g plus T2y, and these are just the magnitude. So I like to do what I call up equals down. So in this particular diagram, I have one vector pointing up, which is T1y, but I have two vectors pointing down, which is f of g and also T2y. So I'm just going to go ahead and move T1y. Just watch the animation here. All right. As long as you don't tilt the components, you can move it. So where it actually touches the sphere, if you like, it doesn't really matter how you draw, as long as your component is drawn in the right direction. It should be okay. All right, so this is T1y. I just moved it over there just so that you can see why this particular statement is true. Why I said T1y is equal to fg plus T2y is true. So here, T1y is pointing upward. I have f of g pointing down. However, I'm also going to move this T2y component over here. So as you can see, if you look from the sphere here, you only have one vector pointing up in the y direction, but you have two vectors pointing downward. But this is a horizontal plane, so the sphere is not moving up or down, it's just spinning in this nice horizontal plane. Okay, so therefore net force in the y direction must equal to 0, which implies that the arrows pointing up must equal to the arrows pointing down. In this case, there's only one arrow pointing up, so that's why that's true. All right, so T1y can be expanded to be T1 sine theta, because it is y, and the theta here once again touches the x-axis. Your opposite leg in this case, which is on the y-axis, would be just sine. So T1y, I broke it down to T1 sine theta, sine of 30. Here, I already know theta, so I'm just going to go ahead and plug in 30 degrees here. F of g, I broke down to mg, and then T2y is just T2 sine theta, which is also 30 degrees. And then from here, I'm just going to plug and chug. Sine of 30 on your calculator is 0.5, m is 3, g is 9.8. Once again, the direction here has already been accounted for, so please keep that in mind. Sine of 30 also is 0.5. It'd be 0.5 of T2. So I'm just going to simplify my work. 0.3 times 9.8 gives you 2.94. And then as you can see here, I have T1 and then I have T2, right, which is the same variables that we have on the left side. So at this point, like I said earlier, you can decide if you want to solve for T2 or T1. It's up to you first. Here, I already have T1 on the left side almost by itself. So I'm just going to go ahead and solve for T1 in this particular work because it's almost by itself. To get it by itself, I'm just going to divide both sides by 0.5 to get T1 by itself. So 2.94 divided by 0.5, and then 0.5 T2 divided by 0.5. So as you can see, whoops, that came up twice, excuse me. So as you can see, the 0.5 in the second term on the bottom and top cancels out. So really, all you have left is just 0.588. So 2.94 divided by 0.5 is 5.88. the 0.5 on top, 0.5 on the bottom cancels out for the second term here, leaving you with just T2. So you notice here you have T1 is equal to 5.88 T2. Well, now that you have a statement for T1, you can just substitute it in the left side for T1. So instead of T1, I'm just going to substitute out for 5.88 T2 plus another T2. So as you can see here, you have a T2 plus a T2, which makes 2 T2. You're not multiplying, so make sure you're careful with the algebra here. So here I have 5.88 plus a T2 plus a T2. T2 plus a T2 is 2 T2. Okay, so to get 2 T2 by itself, I'm just going to go ahead and subtract both sides by 5.88. So if you take your calculator and you take 22.55 minus the 5.88, you'll get 16.62. And once again, the 2 T2 comes from just combining like terms. And in here, to get T2, you just divide both sides by 2. So 16.62 divided by 2 will give you a value of 8.31 newtons. So that is T2. Well, I just found T2 first, but now that I have T2, I can just plug it back into the statement that I derived from the y side. So T1 is simply 5.88 plus T2. Well, I just found T2 as 8.31. So if you add these two values together, you'll get about 14.19, and those are your two tensions. T1 is 14.19, and then T2 is 8.31. Okay. All right. Stay nerdy. Don't be whack.